So the title of the talk is Near Linear Time Approximation Schemes for Steiner Tree and Forest in Low-Dimensional Spaces. My co-author is Yair Bartal at Hebrew University. Now, as you know, a minimum spanning tree of a vertex or terminal set X connects all vertices while minimizing the weight of the tree, where the weight of the tree is the sum of its edge lengths. Now, a minimum Steiner tree does the same, but it may use Steiner points that are not in X. Where do these Steiner points come from? They could come from the ambient space. For example, if we're in Euclidean space, so they could come from all the points in Euclidean space, or they could come from an auxiliary set that's also inputted into the data. So here in the picture, on the left, we have a spanning tree, and on the right, we have a Steiner tree that uses these blue nodes that are not part of the terminal set X. Now, Steiner tree in Euclidean plane is an old problem. It dates back to the beginning of the 19th century, to the mathematician Gergon and to Gauss. It also appeared in the original list of NP-hard problems of Gary and Johnson. And here you can go to a summary of the history of this problem. In terms of approximation algorithms for Euclidean space, so Aurora's traveling salesman framework from 1996 also applies to this problem. It gives a 1 plus epsilon approximation to Steiner tree in time n, time a polynomial in log n, and Rao and Smith gave some improvements. There's also been some other work, but this is the basic approach. Now we're interested in the Steiner forest problem. A minimum Steiner forest for X is inputted a collection of pairs in terminal set X to be connected. For example, in the picture of the bottom, we have two green points and two purple points and two orange points. Each pair of the same color needs to be connected, and you could also have more points of the same color by just linking up pairs. So that means that entire sets of points need to be connected. The output is a collection of Steiner trees that satisfies the demands. And here we have two Steiner trees. One connects the orange point, and another one connects both the purple points and the green points. We want to, of course, minimize the total length of the Steiner trees. Now, this problem is NP-hard to compute. It inherits the NP hardness from regular minimum Steiner tree because you can have all the points in the same set to be connected. For this problem, 1 plus epsilon approximation was suggested in the Euclidean space by Borodel, Klein, and Matthew. It runs in time nearly linear in n. They wrote that they believe their construction can be extended to, or they suggest their construction can be extended to d-dimensional Euclidean spaces, but there's a lot of non-trivial problems that one encounters when one tries to do that. And in fact, Chan, Hu, and Jiang extended it all the way to doubling spaces, which subsume within them d-dimensional Euclidean spaces. Let's take a look at their runtime. The leading term in the runtime is n to the 2 to the d, where here d is the doubling dimension. Okay, so there's a very steep dependence in the doubling dimension over there. I'll just remind you what doubling dimension is. Doubling dimension is a way to measure the complexity of metric space. A doubling constant is the number of half-radius balls necessary to cover a big ball. The doubling dimension is log of the doubling constant. So here in this example, in the plane, I have a big ball, and I've covered it with 8 small balls, and I think that if you can actually do 7. Okay, but that's the idea. You have a ball with a certain radius. How many balls of half the radius does it take to cover the big ball? And this is a measure of metric space in general, a way of measuring metric space. D-dimensional Euclidean spaces have doubling dimension theta d. So the notion of doubling dimension can be seen as an extension of Euclidean spaces to Euclidean dimension to non-Euclidean spaces. Okay, so we recall the 1 plus epsilon approximation algorithms for the Euclidean plane in doubling spaces. And our contribution is, again, in doubling spaces, we give a deterministic algorithm whose runtime is in some ways nearly linear. It has a linear dependence on n, then afterwards a doubly exponential dependence on the doubling dimension squared, and also an exponential dependence on log n. Okay, and the talk will be discussing how one gets a result of this type. Okay, so there's 4 major steps in our approach. Okay, the first step decomposes the master problem, the given problem, into subproblems that have small diameter. Okay, and this is a step that's also was used by Borradaile et al. And we'll discuss briefly what we needed to do to apply this to doubling dimensions. Now, for each subproblem, we create a banyan, and this is really the key to our approach. A banyan is a light graph to which the forest may be restricted, but it gives you a lot of information. You have a graph in front of you, and the forest has to be restricted on that graph, and without loss of generality, you can do this without losing too much in the approximation factor. We then sparsified the Banyan, a technique that hails back to approaches for traveling salesman problem in doubling dimension. So that's by now it's a well-used technique. And then we build a hierarchy on the Banyan and solve Steiner forest using a dynamic program. The quadtree of Aurora is a type of approach in this direction. You place down a hierarchy and use it to motivate a dynamic program. Okay, the first step we said is to decompose the master problem into subproblems of small diameter. Okay, now in this example that I have here, the diameter is much larger than the weight of the optimal solution because in the optimal solution, there are trees that are very, very far from each other. And in the construction of the banyan, this is going to be problematic for us. Okay, we really want to separate this master problem into 2 smaller problems, each one having diameter around the same size, or each one having the solution, optimal solution, larger than the diameter. So Eisenstadt, Klein, and Matthew already in 10 years ago show that the following is possible. If we're given a master problem, the problem is defined by X, the terminal set, and S, the set of Steiner points, we can create subproblems. Okay, the subproblems satisfy that the union of the terminals in the subproblems equals the terminal set. Okay, that the sum of the optimal solutions for the subproblem is not altogether, it doesn't have much more weight than the optimal solution for the larger problem. And implicit in this, even though I don't say it, is they also solve the larger problem. If you solve all the smaller problems, you've also solved the larger problem, although I didn't write that explicitly. Okay, and also the third thing is what's interesting for us. The sum of the MSTs of each small problem isn't much larger than the size of opt. Now the MST is always not smaller than the diameter. So that means that the sum of the diameters of the small problem is proportional to the weight of opt, which allows us to pay some approximation penalty in the diameter. Okay, because the sum of the diameters is proportional to the weight of the optimal solution in the master problem. Okay, so they already show this. The difficulty for us was the runtime. In applying this was the runtime. They show this for planar graphs and show that they can do this decomposition in n log n time. Okay, it wasn't known how to do this in other spaces, so we modified their construction and achieved for all graph time that is proportional to the edge set, the cardinality of the edge set, times log squared times of the cardinality of the edge set. What does that mean for doubling spaces? Well, doubling spaces admit spanners. Okay, if you have a doubling spaces, you can put on it a graph and limit your problem to the graph. The spanner has low distortion, only 1 plus epsilon distortion, not a lot of edges. Okay, the number of edges is linear in n when you take the doubling dimension epsilon to be fixed. And then plugging in this value for the number of edges into our result for general graphs, you get that the runtime is something like n log squared n. So this is fine. You can do this in our setting. Okay, and that is the first step. So the first step says that the diameter reduces it to subproblems where you're allowed to pay something in the diameter. The subproblem, the diameter isn't so big. Okay. The second step, having done that, is the creation of the banyan. Okay, for each subproblem, we need to create this banyan. A banyan is a light graph to which the forest may be restricted. Now, banyans were actually already known for Euclidean spaces, um, a result of Rao and Smith for 98, but that wasn't enough on its own to get Steiner forest, but this is a component that we needed. We needed banyans for doubling spaces. So we showed how to construct a banyan for doubling spaces. The banyan satisfies that the weight of the optimal solution for x restricted to the banyan is bounded by 1 plus epsilon times the optimal solution not restricted to the banyan, plus a small term in the diameter. And because of step 1, we can pay this small term in the diameter. Also, the banyan itself is relatively light. It doesn't weigh much more than the MST of x, and that's important for the dynamic problem. So here in the pictures, you have a complete graph on all the points. The banyan is a subgraph of this with the nice properties that are listed over here. The key is that it's not too heavy, and then the Steiner tree, the solution for the Steiner forest, will be a subset of the edges of that banyan. Okay. The third step, and this is a step commonly used for algorithms with for doubling spaces, is to sparsify the banyan. Okay, this was actually already done by Chan et al., who had an earlier solution for Steiner forest and doubling spaces. A technique was introduced by Bartol-Golub and Krautgamer in a paper in 2016. Okay, what does it say? It says that if there's a dense area in the banyan, so here we have this orange dense area where the edge weights weigh more than some constant times the diameter of the area. So it's known that you can take this set and actually spin it out into its own subproblem, retaining only a single point in the original problem, and that's how the two problems get joined together. And what happens here is that all the trees, Steiner trees of the optimal solution that pass through this dense area, you can actually afford to reroute them through a single point, and they're actually become the same tree. Okay, now there's some additional cost to spinning this out, but because this area is relatively dense, you can charge the cost to the area that's spun out. Okay, so now we have, after these 3 steps, we have a problem that has the following property. Its diameter isn't too big. It's restricted to an underlying graph, a banyan, and that banyan is relatively sparse. Okay, and every ball that you can draw around the banyan, there aren't too many edges there. It's relatively sparse. Okay, having done that, we can now build a ball hierarchy on the banyan and solve Steiner forest using a dynamic program. And then, if you're familiar with Aurora's solution to Euclidean TSP, it's the same idea. You impose some type of hierarchical structure, and then you solve every small area brute force, and use every small area to solve the bigger areas, also brute force, via a dynamic program. Now, our hierarchy has a very, very unique structure that hasn't appeared before, in that if we have here a big ball, okay, in the hierarchy, its children are of various sizes. The children that are closest to the edge of the big ball are very, very small. Okay, the smallest ones have diameter 1 over log n factor of the parent ball. And as you go deeper and deeper, closer to the center, you get balls that are bigger and bigger and bigger, and the center ball is only a constant fraction smaller than its big parents. Okay, so there's this staggering a system of balls, such that the balls near the rim are very, very small, and as you go towards the center, the balls get bigger and bigger. Okay, a nice property here that we can show that every ball has only log n children. Okay, we'll discuss that a little bit more. And then, of course, every child ball is itself decomposed in the same fashion. So if we take every child ball here, it itself will be composed into smaller balls, where near its rim are very, very small balls. And as you get farther and farther away from the rim, the balls get larger and larger. Okay. Okay, now the dynamic program is simplified by two properties, by both the sparsity that we've discussed and by the staggered size. The sparsity says, well, there's the underlying graph doesn't have a lot of edge weight over here. So if you're covering the underlying graph by balls, you're not going to need a lot of balls to cover it. The two things go together. Each ball has only log n child balls. That has to do with the fact that the smallest of the child balls is 1 over log n. Times the size of the bigger ball, and then if you take discrete sizes, the sizes that jump by 2, they're only log n distance scales, and because of sparsity, every distance scale only has a constant number of balls, so you end up with a small number of child balls. You also end up with the property that if you choose your balls carefully, each ball only cuts a small number of banyan edges. Because in every area, the sum of the weights of the banyan edges are pretty small. So you can find a ball that doesn't cut a lot of edges. And that makes the dynamic program easier, because the dynamic program is going to have to go for every child ball and decide what the configuration is, the trees coming in and out. And if only a small number of edges cross that, there are only a small number of trees to deal with. Now, the staggered sizes also limits the number of distinct trees that can be incident on a single ball. Okay, there's two cases to consider. If there's two distinct Steiner trees in the optimal solution are found in the same child ball near the border, there aren't a lot of child balls near the border. Okay, and they're very small. So you can actually afford, in the picture on the left, to connect those two trees. And now they're one tree, makes the problem much easier. You don't have to worry about a lot of trees going in and out. There's one tree that's going in and out several times. Okay. Now, if they're found in a child that's farther away from the border, like in the picture of the right, on the right, so in this case, each of these trees actually traverses quite a bit from the outside until it gets to the inner ball. And you can charge against these paths. It happens to be that you can't say for sure that they're connected inside the inner ball, but you can say that they're connected somewhere in the entire graph. And so again, these, even though you can make these into the same tree, you can connect these and they're the same tree. And again, it limits the number of different possible trees going in and out. It makes the dynamic program less costly. So, very, very high level, for log n child balls, we're going to need to compute every possible configuration. For each edge crossing into the ball, we need a record of the Steiner tree that this edge is a part of, and also for the other edges of the ball, which ones are connected, and are they connected outside or inside? The total time ends up being exponential in the number of children. So log n squared, you have to go down another level. Okay, so it's exponential in the number of children squared. Okay, log n, that's where you get the leading term. Okay, now of course there are a lot of details here, and unfortunately time constraints don't permit me to go deeper into the 4 steps. So I decided one thing that interests me in the construction had to do with something that we encountered while constructing the banyan. So again, I don't have enough time even to explain the banyan from beginning to end, but there's, let's say, half of the construction of the banyan I do have time to explain. And that's the following. Let's define a proper Steiner binary tree to be one where the internal nodes are all Steiner points, so here they're blue, and the leaves are all terminals. Now, a proper Steiner tree decomposition of a Steiner tree is a set of proper binary Steiner trees connected at their leaves, like in this picture. So you have these 3 proper Steiner trees connected at their leaves, and that's the that's the way that we view the original Steiner tree. Basically, all these together form a Steiner tree. And of course, every Steiner tree can be trivially represented in this fashion. But what's interesting here is that every Steiner tree can be decomposed into a set of shallow, proper Steiner trees. So not only is it possible to decompose a Steiner tree into proper Steiner trees, but you can do it even if you want all the proper Steiner trees to be very, very shallow, and you lose something. Okay, you lose the weight goes up a little bit, but it can be done, and it's interesting. So there's some epsilon. The depth is only 1 over epsilon, and the weight of the Steiner tree increases by a factor of 1 plus epsilon. Okay. So let's consider the following decomposition step for any Steiner tree. We're going to delete the edge here connecting V and W. We'll reroute the parent U to X, okay? So that's not a loss, it's connected to X anyway via V. But we gain that we deleted the edge VW. Now we have two trees that aren't connected, but we'll have to connect them. So that's what we pay. Okay, so what do we gain? We deleted the edge VW and inserted this green arc to reconnect the tree together. So there's some cost associated with this, but we're going to keep on doing this as long as the cost is relatively small. As long as the cost of joining those disjoint trees, that's the little green arc, is smaller than the weight of the edge that we deleted, that connected V and W, plus a small factor times the weight of the proper Steiner tree that W was a part of. So we picked up a little bit of cost, and we're going to assign that cost to the proper Steiner tree of W. Okay, so we can keep on doing this. If we do this in a smart way, we can just keep on doing this until we've removed all edges that we needed, and the charging argument shows that this increases the total weight of the Steiner tree by very, very little. Okay, now having executed these decomposition steps over and over again, we have that for any subtree rooted at some vertex V, the sum of the weights of the two edges leaving that is, of course, can only be greater than the child tree distance to connect them. And it's greater than the max of these two quantities. That's simply, otherwise we would have deleted it. In any event, it means that the weight of the proper subtree grows by a constant factor at every level just because of the edges. Okay, it means that the edge Vx plus the weight of the edge Vw is actually quite heavy. Okay, they're quite heavy. They're a constant factor of everything that's beneath them. Okay, so actually, as you go up, you're picking up edges that causes the weight of the proper Steiner tree after this decomposition to grow exponentially. Okay, and that's what we said. We started with a Steiner tree. We decomposed into proper Steiner trees whose weight grows exponentially as you go bottom up. Okay, well, if the weight grows exponentially as you go bottom up, that means that subtrees that are very, very low down have weight that's negligible when compared to the weight of the tree as a whole. Okay, so after going down about 1 over epsilon, 1 over log 1 over epsilon levels, the weight of these trees, of these subtrees that are far from the root, is very, very small. Okay, so in fact, you can afford to get rid of them, okay, get rid of these Steiner subtrees, and connect their root straight to a leaf and all the leaves straight to each other, which means that these are improper subtrees, right? The proper Steiner tree is just what remains, and it has only 1 over epsilon log of 1 over epsilon levels. It's shallow. Okay, so every Steiner tree can be decomposed into a set of shallow proper Steiner trees. And that means that each of these trees has only a constant number of vertices, and this was a key ingredient in constructing our Banyan. Okay, I'll conclude now. We have an algorithm for doubling spaces. It's deterministic, it's near linear runtime, and it's composed of 4 steps. Each one is pretty intricate on its own. Okay, thank you very much for listening to the lecture. Okay, and I hope that you found this interesting and might consider reading the paper.